Alright, in this video we're going to be coding example number 3 from our projectile motion coding assignment. And we have a ball that's being fired off at an angle of 40 degrees above the horizontal with a speed of 20 meters per second, and it's going to hit a wall that's 25 meters away. So we want to animate this using GlowScript. So I'm going to open up our GlowScript window over here, and I'm going to steal something from another program over here where I'm going to just put a little bit of a canvas down. So I'm just going to pull that over here and put that in here. So make the background white. We'll call projectile motion assignment number assignment, and then example 3. And we'll fix the centering bit a little bit later on. We need to have a ball, obviously. A ball will be represented with a sphere. We'll put the ball's original position at 0, 0, 0. That makes sense at the origin. The size we'll just say is just 1, 1, 1. Make the ball just red for color. And then we're going to be adding a trail to it, but I'll do that a little later on. Let's just make it work first. So next thing is I guess we can add an axis. So my x-axis is going to be represented by an arrow. And we have pos equals vec. And we're going to have that also start at the origin. But the shaft width, I guess we'll just leave that as, I don't know, 0.1. And axis equals vec. We're going to have it stretch up. What position does it start at? The ball is going to be going 25 meters horizontally, so we need to have the x-axis at least go beyond 25 meters. So we'll make it go 30 for the x-axis, 0, and 0 for the y and z-axis. And color equals color dot blue. Okay, and similarly we're going to do a y-axis. I'll just copy that, change that x to a y. Start at the origin, same shaft width, but except we're now going to make it stretch vertically upwards at 30. Let's just take a quick look and see what that looks like. Okay, there we go. There's the ball, and there's my x and y axes. Okay, next. We need to give the velocity or the position. I guess set the initial position of the ball. So we're going to indicate R, I guess, is my position of the ball initially. Now I'm going to choose, just to kind of save a bit of space in my code, I'm going to define that position as ball.pos. Now technically what I'm doing is I'm setting, I could, if you want, you could go x0 is ball.pos.x, and then you could do y0 equals ball.pos, that's supposed to be a pos, dot y. Or alternatively, you could just do r0, and now that basically is giving you setting r as a vector to be equal to essentially whatever you have for x initial and then y initial and z initial. So in this case it would be 0, 0, 0. Okay, but just kind of pointing that out, you have kind of cool ways to do it. You can set them up as scalar amounts, or you can set it up as a vector quantity. So I'm going to choose to just kind of save some space to get rid of that and just basically define it as a vector, the initial position. And really I probably don't even need it because everything's being set at 0 anyway initially. But let's say we want to put the ball a little bit higher later on in the problem and see what that does. We can change this position of the ball. The next thing is the velocity vector. So the initial velocity, we're also going to set that up as a vector. So we're going to use a vec. Okay, and give it an x and a y and a z. So going back to our projectile motion assignment, we see that it's going at 20 meters per second at an angle of 40 degrees. We need to break that up into components. So you can think of it as this is really the horizontal velocity would be 20 multiplied by the cosine of what angle? 40 degrees. Ooh. Now, I should point out that the computer thinks in radians, so it's not going to understand 40 degrees. So you need to tell the computer what that is in radians. So the quick way to converting from degrees to radians is use this function called radians 40. So now that's going to convert the 40 degrees into a radian amount, and then it's going to take the cosine of that and then multiply by 20 because that's the speed of it. So we're doing essentially V0x is V0 times cosine theta. Now we're going to do the same thing for the y, which is 20 times the sine of the radians of 40. And then z would be just 0. Okay? So, I mean, another way you could do it is at the beginning just, set, v equal to 20, and then angle equal to 40, and then, or you could maybe call it angle to be radians times 40, and then you can build them in here, this function. But I'm just going to try to keep it all built into here. This is the x velocity and the y velocity. Next thing is our acceleration. Let's make that a vector as well. It doesn't have an acceleration horizontally, so that's 0, but it does have a vertical acceleration of -9.8, and we're not having an acceleration on the z-axis. So we only have a vertical acceleration, ay equals -9.8. Now again, you could, go ax is 0, ay is -9.8, and then kind of solve it that way. But I'm trying to save space, so I'm going to treat them as vector amounts. Okay, of course, we probably want to put t, our time starts at 0, and then have some increment. Let's go with like 1/100th of a second. Okay. So I think we're now ready. Let's just make sure this all sort of makes sense. All right, no errors. Okay, we're going to make that ball basically fly through the air. I'd probably put a wall in here as well. The wall is located 25 meters away. So let's throw that in there. So maybe I'll just put a wall equals box, pause, vec, and it's going to be located 25 meters away, 0, 0, and then size will be vec, and let's give it, some vertical height, like a little bit wide, and then vertical height of, 5, and 0. That's 1 here. And color equals color dot green, I guess. All right. Now let's take a look at what that does. Yeah. The only thing is that, remember I set that position at 0 here for the y-axis. So see, it's being set at 0, moved, shifted 25 over to the right, but vertically we need to kind of change that a bit. So maybe if we shift this, see we have this going up 5, maybe we'll make that 10, but then move the position vector up 5 units, so it's half of 10. Let's see what that does. So there we go. We got a wall here. The middle of it's 5 units up, but it's 10 high. Okay, so we're going to fire a ball and see where it hits onto this wall. Might need to make that wall a little bit bigger. Okay, so let's start our while loop. And we're going to basically fire that projectile until it gets to a position of 25. So that's for our condition here. We need to keep moving the ball's position in the x-axis, keep going until you get to 25. When you get to 25, or just under 25, we're going to then exit out of the loop. So the rate, it's going to slow down our animation so it doesn't go too quickly, rate of 100. I always do basically the inverse of what I use for dt. Next is now we're going to change and update the x coordinates of our ball and the y coordinate. Now, of course, again, if you did x sub 0 and y sub 0, then you'd have to both update x and y individually. But because I'm treating the position as a vector, I'm going to update x, y, and z all at the same time. Now, z is not changing, but the x and y are changing. So what we're going to do is we're going to do ball.pause equals r0, that's like the initial position, plus v0, okay, so that's the initial velocity of it, multiplied by t plus 0.5 times a times t. So I'm using basically x equals x0 plus v0 x times t plus 1/2 at squared. But it's going to do it basically, calculate it for the x and the y and the z and do all 3 calculations at once. And that's the beauty of doing this all in just one line. And then we want to update the velocity. So the initial velocity maybe is going to be v equals v0, but then at some point we're going to set, oh, we probably don't need to do that actually. We could just go v equals over here v0 plus a times t. Right, and then of course we've got to increment time, so t equals t plus dt. Okay, let's take a look and see if this is kind of showing what I wanted to do. All right, and boom. Oh, and the walls, it's kind of, I bet the ball is entered inside that wall here. And maybe I want to move that wall just a tad over here. Maybe make it like 26, and so we can see the ball basically just kind of sticking to the wall here. There you go. Okay, so we're good. We're in business here. Now, the next thing is to do some graphs so we can see what's kind of happening here. So I'm going to steal again something from an earlier program that I wrote where I had graphs. And I'm going to produce two graphs. I'm just stealing this from an earlier coding here. I have graph 1. I've got the graph, I've got the width and the height. I kind of like that, time. And then this is position. And I'm going to make my X max. I don't know how long it takes, so I'm going to have to adjust this a little bit. My vertical height is 25. It might have to go a little higher. I don't know. Let's just say, I don't know, 5 for now here. So this is basically X min and X max is our time. It starts at 0 time and goes to, say, 5 seconds. But I don't know what that is. I might want to, print, I guess, that time and see what that is. So if I run the program here and see, well, 1.65. So I need basically a little bit more than, say, 1.65 seconds. So maybe I'm going to set that time to be 2 seconds here. Okay. Maybe I want to print the ball's position. All right. And so if I print that now, I can see at the end of it, it ends up having an X value of 25.12 and a Y value of 7.9. So I probably need to at least have horizontally go to 30, and vertically I should probably be going up to 10 or something, or maybe a little bit more than that. So we're going to make this go up to 20 is fine, and then for velocity, what's the velocity here? Let's take a look at that velocity. The velocity, v. So what is that going to be at the end of this? And so again, those kind of values, maybe up to 25. So we're good, but we need negative velocities. So we need to change this a little bit and add negative 20 to, I don't know, positive 20 or 25. Let's just take a look and see what happens. So we've got the graphs defined in here. Of course, we now need to come up with a bunch of series we're going to be plotting. So I'm again copying some code over here. I have over here, I'm going to be plotting the X position in blue and the X velocity in blue, and then I have the Y position and the Y velocity in green. And I'm going to be putting, let's see, the X and Y positions in graph 1 and the X and Y velocities on graph 2. And the next thing I need to do in here, I need to be plotting what I want for those series for function 1, function 2, function 3. So again, I'm stealing this from another code I have. So here I'm going to be plotting f1 t ball.pos along the x, t ball.pos along the y, and then I'm plotting the x velocity and the y velocity here. Okay, so let's take a look and see if that does what I'm hoping it will do. All right, and yeah. Okay, I guess I could probably stretch that x one a little bit higher. Okay, so maybe not 25, but like 30 or something like that. That's not bad. You can see the velocity is starting out here, and then it's going down here and becoming negative. So I probably go to 10. Just a little few things that we can fix up here. Change that to say 30, and we don't need to go down as low here. Maybe negative 10 and maybe 20 or something like that. Okay, so just a little bit of modifying to put in here. So this is, you can see our horizontal position is going in a straight line, and we're getting a nice parabola out of the vertical position. Okay, so what else can we do? Well, another thing we might want to add is put a trail that follows the ball. So we add that in here. I'm going to pull this again from another bit of code here. I'm going to add in a line here where I add make trail equals true, or the points, and we're going to just do intervals of 10 because remember it's printing basically a lot of dots if I do it for every single one. So let's run this again, take a look at it, and you can see the little dots that are forming behind the ball. Okay, and what else? What else can we do? Of course, we need to answer some of the questions in here, and we have how long is the ball? Does it take for the ball to reach the wall? So we're going to just put a output in here at the very end of this. a little print statement here. Print the ball takes, comma, t, right? Which actually technically goes a little bit one increment over it, so minus dt, technically speaking, and then seconds to reach the wall. Right, and that will print out correctly here. And that should be down just underneath these graphs, so it'll output it over here. You can see that the ball takes 1.64 seconds to reach the wall. What else do we have to do? We have to print out the how far above the release point it is. So that would be the vertical position. So maybe I'll just steal the wording in here. Yeah, so we'll just go over here and type in another line in here. Print the ball reaches a height of, and that's the ball dot pause dot y, its coordinate at that point, meters from the ground. Okay, so again I can run it and take a look at what happens here. And so you get the idea of what we have. It's pretty straightforward. You're just plotting these things and getting the distances. Of course, I can round that. There's a lot of digits here, so I might want to round it. And so I might go round. We'll take this and maybe multiply by 100 and then divide by 100, so I get like 3 sig figs. And yeah. Okay, nearly done. I guess you can probably finish the rest of it yourself. Okay, you can obviously just learn it. Well, why not finish it here? What is the horizontal and vertical components of the velocity? So again, what you're doing, you go ahead and do this. What you should be able to do is just find out what the velocity along the x-axis is, which is basically vx, and the vy velocity. That. You just simply write that out. Okay, and when it hits, has it passed the highest trajectory? Well, hopefully you can see that from the code. When you're writing the code, you can see, like, when does it reach the very apex of that path? And it looks like it starts coming back down, right? So it already has reached the top of its path, and then it eventually actually hits the wall as it's coming down. You can tell that too because the velocity is now becoming negative, and so the ball is actually coming down. So yes, to answer this question, when it hits, it has, yes, passed the highest point of its trajectory. Okay, that's a long explanation, but hopefully you follow that. You can do this yourself. You have to be able to code this by yourself on a test, the right code. All right? Okay, that's it for this problem.